The CANDU nuclear reactors that were designed by Atomic Energy of Canada Limited and Ontario Hydro and Canadian General Electric Company Limited in Canada are different from the two most widely used nuclear power reactors in the world, the pressurized water reactor, PWR, and the boiling water reactor, BWR. The most obvious visual difference is that the fuel in a CANDU reactor sits in horizontal channels, while the fuel in the other reactors sits in vertical channels. The main reason why CANDU fuel sits in horizontal channels is to allow the fuel channels to be replaced with new fuel while the reactor is still operating. The reason why the fuel is replaced in CANDUs while the reactor is still operating is because CANDU fuel is not enriched. Enriched fuel can provide the reactor with a consistent amount of energy for a longer time period than unenriched fuel. Therefore, enriched fuel does not have to be removed from the reactor as frequently as unenriched fuel. Even though shutting down the reactor during refueling results in a sustained power loss, this is acceptable with enriched fuel because the reactor can run for a long time when a new batch of fuel is inserted into its fuel channels. Therefore, the fraction of time the reactor is producing power is acceptable. If this type of refueling was attempted for a reactor that runs on unenriched fuel, the overall fraction of time the reactor produces power would be too low. This would be unacceptable. This is why a reactor with unenriched fuel should be designed to be refueled while the reactor is still running. This is exactly what is done for a CANDU reactor. The reason horizontal channels were selected for CANDU reactors is because it is easier to refuel the reactor while it is operating with horizontal channels than vertical channels. With horizontal channels, there is no need to attach the individual components within the channels, called fuel bundles, together for stability. Vertical refueling while the reactor is operating can still be done, but for simplicity's sake, horizontal channels were chosen for CANDU reactors. Pressurized water reactors contain enriched fuel and vertical channels. In PWRs, refueling is done in batches during periodic outages when the reactor is shut down. A major difference between pressurized water reactors and CANDU reactors is that the moderator of a PWR is significantly pressurized, while it is only very slightly pressurized above atmospheric pressure in a CANDU. Pressurization is done to reduce the size of the reactor vessel in pressurized water reactors. It is also done for simplicity because, in this way, the coolant and moderator do not have to be separated in PWRs. The coolant and moderator will now be defined. The coolant has a self-explanatory name. It is the fluid that cools the nuclear fuel that absorbs heat from it in the process. After absorbing heat, the coolant flows from the reactor to the steam generator or boiler to generate steam to be used in electrical power production. In a pressurized water reactor, the coolant is regular water, also known as light water. The term light water will be explained shortly. The moderator is required to increase the amount of power that can be produced by the reactor. The moderator moderates the speed of the neutrons that are moving through it. The speed of the neutrons decreases as the neutrons collide with the atoms of the moderator. Slower neutrons more effectively fission with nuclear fuel. This is how the reactor power is increased by a moderator. Water in nature actually comes in different forms with the same chemical composition. This is because chemical composition is determined by the number of protons and electrons an element or compound possesses, but not the number of neutrons it has. The two most prominent forms of water differ by the type of hydrogen that exists within them. Light water, what we typically refer to as regular water, has normal hydrogen atoms with no neutrons, and the other form of water contains hydrogen that has one neutron. The extra neutron makes this form of water heavier. Since most of the mass of the water molecule comes from the oxygen atom, the overall mass is only slightly increased, by 10%. However, this mass increase is noticeable, and so this form of water is known as heavy water. For a given element, forms of it with different numbers of neutrons are known as isotopes of that element. In nature, there are roughly 6,500 atoms of normal hydrogen for every one atom of heavy hydrogen. The heavy form, or isotope, of hydrogen is also called deuterium, while the normal hydrogen is known as protium, although often protium is just referred to as hydrogen. There is another naturally occurring isotope of hydrogen called tritium that has two neutrons. Tritium is found in extremely small concentrations in nature and is produced when cosmic rays collide with gases in the atmosphere. Tritium, unlike protium and deuterium, is radioactive. Hydrogen is the only element that has common names for its isotopes. Isotopes of hydrogen containing 3, 4, 5, and 6 neutrons have been synthesized in laboratories, but they are highly radioactively unstable, with half-lives of tens to hundreds of yoctoseconds. The ability to moderate or slow down neutrons depends not only on the chemical composition, but also the number of neutrons of the atoms in an element or compound, in other words, on the specific isotopes present. Oxygen neither absorbs nor scatters very many neutrons. Protium aka normal hydrogen, on the other hand, is very good at slowing down neutrons and also absorbs them to some extent. Deuterium is good at slowing down neutrons, but not as good as protium. However, deuterium does not absorb very many neutrons. It absorbs far less than protium. The abilities of light water and heavy water to slow down or absorb neutrons are therefore dependent on the hydrogen isotope within both of them. Since light water can slow down neutrons better than heavy water, it is possible to adequately moderate the population of neutrons within the reactor with a smaller volume of it than would be possible with heavy water, everything else being equal. Furthermore, the chance of undergoing fission is greater with more targets available. Conversely, neutrons that are absorbed or captured can no longer undergo fission. Therefore, the penalty in reactor power output that comes from light water absorbing more neutrons than heavy water is offset if light water is used in a pressurized water reactor containing enriched fuel, since with enriched fuel there are more targets available for fissioning. Although the use of light water makes the reactor size smaller, the reactor vessel it is contained in would still be large if the light water was not pressurized to some extent. This is because pressurized water has more closely spaced water molecules, and therefore more densely packed hydrogen atom targets for the neutrons to hit. Thus, a neutron is more likely to be quickly moderated and less likely to escape the reactor. Therefore, the light water moderator and its vessel are pressurized to a significant extent. Pressurized water is also desirable for the coolant since water remains a liquid at higher temperatures when pressurized. High temperature water has good heat transfer properties and retains a high amount of heat. Since the moderator and coolant were both required to be pressurized, for simplicity, the PWR designers chose not to separate them. In a CANDU reactor, heavy water is used as the moderator. Because the CANDU reactor fuel is unenriched, there are already less targets for neutrons to fission with than in a pressurized water reactor. Therefore, if light water were used in a CANDU reactor, there would be too great a neutron loss and not enough targets to produce enough power. This is why a heavy water moderator is used in a CANDU. The heavy water is obtained at facilities that process large volumes of natural water to separate the tiny fraction of heavy water that it contains. Since, on average, the heavy water does not moderate the neutrons as well as light water, CANDU reactors require a larger volume of it to moderate the neutrons to a high enough extent that enough power is created. Even if the moderator in a CANDU reactor was as pressurized as in the pressurized water reactor, the volume of heavy water required would still be greater than the volume in a light water reactor. When the CANDU reactor was first being designed, it was difficult to manufacture pressurized vessels of a great enough size and structural integrity to hold this amount of pressurized heavy water. Therefore, in a CANDU, the moderator is only very slightly pressurized and it is separated from the coolant. In both the CANDU and pressurized water reactors, the coolant is kept at a high pressure so that it can contain a greater amount of energy while remaining a liquid. As mentioned, in a PWR, the moderator and coolant are not separated. In a CANDU, the pressure of the coolant desired is achieved by pumping high-pressure heavy water through pipes called pressure tubes that run through the horizontal fuel channels. These fuel channels penetrate a cylindrical vessel with its flat sides facing the horizontal direction, called a calandria, that is filled with the moderator. The moderator flows around the outside surface of the channels and remains separated from the coolant inside them. There are hundreds of fuel channels and pressure tubes per reactor. Although the incorporation of pressure tubes complicates the design compared to PWRs, it adequately solves the heavy water pressure vessel problem mentioned earlier for CANDUs. The pressure tubes contain the fuel and are filled with heavy water rather than light water. Heavy water is used because this water is right next to the fuel where fissioning is happening. The fissions cause new neutrons to constantly be produced, and the coolant must minimize the amount of neutrons it absorbs before the neutrons move to the moderator, again, and move back from the moderator to the fuel. Again, given that fuel in CANDUs is not enriched, there would be too many neutrons absorbed in this fashion if light water coolant were used in CANDU pressure tubes. This is why heavy water is necessary in the pressure tubes. In a CANDU reactor, the pressure tubes are connected to pipes that transport pressurized heavy water to and from the steam generators. These are called feeder pipes because they feed the steam generator with the hot water from the reactor and then feed the same water that traveled through the steam generator back into the reactor. The feeder pipes leaving the reactor, called outlet feeder pipes, connect to an outlet header that then connects to the steam generator. The water leaving the steam generator connects to an inlet header, which leads to feeder pipes known as inlet feeder pipes that enter the reactor. In most CANDU reactors, 1/4 of the feeder pipes at one side of the reactor connects to one outlet header at that side, and another quarter connects to another outlet header at that side. The other half of the feeders at that side of the reactor connects to two inlet headers, 1/4 of the total to one and 1/4 to another. After the water flows through the steam generator, it is pumped through one of two inlet headers and back to the same side of the reactor face. In this way, there are two overall loops leaving that side of the reactor face and the same two loops entering the reactor face. Because everything on the other reactor face is a mirror image of the first described, and because the feeder pipes on both ends are connected by fuel channels, in this configuration, there will be two loops exiting and entering the fuel channels on the other reactor face as well. Therefore, overall, there are two coolant loops in most CANDU reactors. The Bruce reactors in Canada are different because they have only one outlet header on either side of the reactor face. This means that water from any fuel channel can ultimately end up in any steam generator. This means the coolant system is contained in a single closed loop. There are still two inlet headers at either reactor face at Bruce. Among the operating CANDU reactors, there are a variable amount of steam generators and pumps. Specifically, in some designs, multiple steam generators/steam drums are connected to one outlet header and multiple pumps pump water to one inlet header. In other designs, there is a 1-to-1 ratio of both steam generators to outlet headers and pumps to inlet headers. Only the Bruce reactors contain steam drums. In a PWR, the water flows out of the reactor through an outlet nozzle and through a pipe to the steam generator. After exiting the steam generator, the water is pumped back through another pipe to the reactor vessel. The vessel, first pipe, steam generator, and second pipe form a loop for the coolant. PWRs contain either 2, 3, or 4 separate loops with a variable amount of steam generators and pumps. All the loops still feed into and move out of the same reactor vessel, however. The system transporting the coolant mentioned above is known as the heat transport system for the CANDU and the reactor coolant system for the PWR. As evident from the short descriptions above, there is less complexity associated with this aspect of the PWR design than in the CANDU design. The steam generators, or boilers, in CANDUs and PWRs are similar. In the steam generator, there are thousands of small tubes that follow an inverted U-shape to take the water into and out of the steam generator. Heat is transferred through the walls of these tubes to light water on the outside surface of the tubes that turns into steam. The steam is used in a steam turbine and generator combination to produce electricity. After exiting the last turbine, the steam then flows to a condenser. Inside the condenser, there are tubes that a different loop of cool, less pure, light water called condenser cooling water flows through. The steam transfers its heat from the outside surface of the condenser tubes to the inside surface that contains the condenser cooling water. Since the steam has already flowed through multiple turbines, its heat content is relatively low as it enters the condenser. This is one reason why the condenser cooling water does not heat up substantially in this heat transfer or exchange process. The other reason is that a relatively high volume of water flows through the condenser cooling pipes. For these reasons, the condenser cooling water can be transferred to a body of water without increasing the body of water's temperature to a point where it would significantly affect the environment. Alternatively, condenser cooling water can exchange the heat that it absorbed in large cooling towers. The condenser cooling water is cooled in these towers, and as condenser cooling water is cooled in these towers, steam is produced that flows to the atmosphere directly. No CANDUs use cooling towers, but they are used in PWRs. The steam that came from the turbine and has now been turned back to light water is then reheated and pumped/fed back to the steam generator to form a closed loop. The water is known as feed water at this point. Also, since this loop is distinct from the heat transport loop for CANDUs or reactor coolant loop for PWRs that flows through the reactor, it is known as the secondary side. The heat transport/reactor coolant loop filled with heavy water in CANDUs and light water in PWRs is known as the primary side. In summary, in a CANDU reactor, the coolant that directly cools the fuel flows in the following loop, starting in the reactor core, from the horizontal fuel channel to a feeder pipe, to an outlet header, to a steam generator, to a pump, to an inlet header, to a feeder pipe, and back to the fuel channel. Most CANDU reactors have 2 of these loops, while a few have 1 loop. Each CANDU contains hundreds of fuel channels and feeder pipes. And another interesting fact, the Bruce reactors in Canada are currently the site with the largest power output of any nuclear generating station in the world. And there are 19 power reactors currently operating in Canada. Most of them are in Ontario, and one of them is in New Brunswick. There used to be one in Quebec. Thank you.